In this series about waves, so far we've looked at how waves propagate and also what happens when a wave meets another wave. Now we're going to look into what happens when a wave hits an obstacle. We'll first look at the simplest explanation, which you probably know from high school. Then move on to the general case and finally a very specific case called frustrated total internal reflection, which in quantum mechanics is called tunnel effect or quantum tunneling. The tunnel effect is one of those spooky quantum things where a particle breaks through a barrier which it should not be able to cross. Without quantum tunneling, protons wouldn't be able to cross the Coulomb barrier and there would be no nuclear fusion in stars. Alpha particles wouldn't be able to escape the potential barrier of the nucleus and there would be no alpha radiation. Within the DNA molecules, proton tunneling is a key effect enabling spontaneous mutation, and so on. And at the end of this video, you will be able to understand the basics of quantum tunneling. Because it's not some quantum magic, it's just waves doing wave things. The easiest way to start off is using Huygens' principle, which states that every point of a wavefront can be considered the source of an elementary wave, and the sum of those elementary waves is the new wavefront. What happens when a wave hits the interface to an obstacle? These are Huygens' own sketches, but since we do video here, we can look at an animated version. A part of an incident wave is reflected, and when we do a proper construction like Huygens did, we find that the angle of incidence equals the angle of reflection, the law of reflection. With a spherical wave, it looks like this. We can see the exact same thing happening in this picture, where the blast wave of a nuclear explosion is reflected off from the ground. The part of the wave that penetrates into the obstacle will in general move on with a different velocity. In the case where the wave is slowed down, like light in water for example, it will look like this. This simple difference in wave speeds alone will cause the wave to change direction, an effect which we call refraction. And again, we can do a proper construction and find the exact angles and everything, and this will give us Snell's law of refraction. And with this we were already able to derive a lot from this simple principle alone. But if we want to learn more, we need to go deeper. For a light wave specifically, we can write down all proper equations, taking into account the wave has a parallel and a perpendicular part to the plane of incidence, and everything needs to connect properly, etc., etc. This is a lot of laborious math, but eventually this gives us the Fresnel equations. These are a complete description of the wave's behavior at the interface. One more thing we can calculate is which fraction of a wave is reflected and how much is transmitted, depending on the angle of incidence and how much the material slows down the wave. What we can see here is that the amount of light that is transmitted is really high when it falls on the surface with a small angle. But for angles of around 90%, almost all light is reflected. This means most surfaces are very good at reflecting light for large angles, which can be easily seen in some examples. Now, when we look at light going the other way, so from a dense material to a less dense one, for example, a light beam crossing over from water into air, the beam will move faster after crossing the interface, which will look like this. At a certain angle, this will create a situation where the transmitted wave will move along the surface, which means that there will be no transmission at all. All of the beam will be reflected. A total internal reflection. This will on the one hand give you pretty awesome pictures like these. But it can also be used for technical applications. For example, the glass fiber cables that carry our internet signals. We can also see the effect in the Fresnel equations. At a certain angle, transmission goes down to 0 and reflection goes up to 1, meaning 100% will be reflected. There is a caveat though, a seemingly small but significant one. We can see, both in experiments but also in the Fresnel equations, that the totally reflected wave does not simply stop at the interface. Instead, it penetrates into the medium for just the tiniest of amounts before it is reflected there. This is called the evanescent wave, and it actually is decreasing exponentially fast. So after just a few wavelengths, it becomes 0 for all practical purposes. Also, it does not carry any energy beyond the interface, as all of it is eventually reflected back. So, a totally reflected light wave moving from a piece of glass into air only penetrates for a few hundred nanometers into the air before being totally reflected back into the glass. But if you place another piece of glass within range of this evanescent wave, a small part of it can propagate to the second piece of glass and continue moving there. And again, there is absolutely no magic in this. The wave simply decreases exponentially, but then reaches another medium where it can persist and move on. And that's what's called a frustrated total internal reflection. It can easily be demonstrated for light and for other waves, and it also has some technical applications in optics and electronics. And that's where we come back to quantum tunneling, which is just a frustrated total internal reflection, but for matter waves instead of for light waves. A matter wave or wave function in quantum mechanics is basically just a measure for where you can find a quantum particle, like an electron or proton. Where the matter wave is high, the probability to find a particle is also high. And that's exactly what happens for alpha decay, for example. Alpha particles are made up of 2 protons and 2 neutrons and can be found within the nucleus of large unstable elements like uranium or radium. The alpha particles are bound by the strong nuclear force and should not be able to escape the nucleus. However, because they are quantum objects and thus have a wave nature, their matter wave can tunnel through the potential wall, decreasing exponentially as it does so. With a low probability, a matter wave can tunnel out of the nucleus and the alpha particle is thus emitted. Alpha radiation. Sometimes quantum effects are really rather mysterious and have no classical analogy, but sometimes they're just a wave doing wave things.